The word law sounds confident, final, as if reality signed a contract and agreed to follow it forever. In physics, the word is used with that same seriousness, but without any assumption of authority behind it. No one enforces a physical law. Nothing checks compliance. There are no penalties handed down for violation. The law holds anyway. That alone deserves attention. There is no built-in requirement that the universe behave consistently. Nothing demands that the same setup, repeated at different times or places, must lead to the same outcome, and yet it does, with reliability strong enough that entire technologies, predictions, and measurements depend on it without hesitation. A physical law is not a command given to nature. It is a regularity discovered through repeated failure to find exceptions. Drop an object, heat a metal, charge a capacitor, send light through glass, change the location, the time, the observer, the surrounding conditions. The relationship repeats, not approximately, not most of the time. The same connection appears again and again. That repetition is the strange part. Physical laws do not explain why the universe behaves this way. They describe how reliably it behaves this way. Take gravity. Objects accelerate downward at a predictable rate near Earth. The law does not instruct the object to fall. It states that whenever mass and distance appear in that arrangement, the same outcome follows. The law is a compressed summary of behavior written after observation. Physics does not invent laws and impose them on reality. Physics notices that reality refuses to vary in certain ways. A law is what remains when preference, intention, and opinion are removed, leaving only what repeats no matter who checks. This leads to a consequence people often overlook. If something violates a physical law, it does not qualify as rare or unusual. It simply never appears in experiments, regardless of how carefully the conditions are arranged. That is why physical laws feel absolute. They are not supported by authority. They are supported by every failed attempt to break them. At the same time, these laws are restrained. They do not specify everything that will happen. They limit what cannot happen, regardless of clever design or effort. That restraint is exactly where their strength comes from. Taken seriously, laws stop resembling rigid formulas and start resembling the framework holding everything else in place. And that leaves a question that refuses to disappear. If the universe follows laws so reliably, where do they come from? And why does nature obey descriptions written by creatures inside it? That tension sits at the center of physics, and it does not resolve easily. That question stays in the air because the word law quietly pushes the mind in the wrong direction. A physical law often sounds like a powerful rule running the universe from behind the scenes, something active, something in charge. But at the deepest level, a law is none of those things. A law is a relationship. More exactly, it is a relationship that stays the same while everything around it changes. That is what separates a law from a coincidence. Materials can change, locations can change, sizes can change, conditions can change, and yet the same connection between quantities keeps showing up. The law does not live inside the object being studied. It lives in how measurements stay linked across many situations. This already pushes against how people usually think about rules. Rules often sound like instructions. Do this, avoid that. Physics does not operate that way. Objects do not check a rule book before behaving. Nothing pauses to see whether it is allowed to move. The law is never consulted. The law is written afterward. What physicists actually track are numbers, distances, times, masses, charges, speeds. One value is changed, another responds, and the search is for a link that refuses to disappear. When that link survives every attempt to disturb it, It earns the title law. So a law is not something the universe follows. A law is something the universe never contradicts. That difference changes how the whole subject works, because it means laws do not push events forward. They sit above events, describing how behavior stays tied together across many cases. This is where everyday thinking tends to slip. It feels natural to say a law causes behavior. Gravity causes falling. Electrical laws cause current. But the direction is reversed. Objects behave first. Laws are written later to describe how that behavior stays connected across different setups. The law describes consistency, not control. A simple example helps. Take a spring. Pull it a little, it resists a little. Pull it more, it resists more. Double the stretch, double the resistance. Change the spring, and the exact numbers change, but the link between stretch and force stays. The law is not hiding inside the spring deciding how to respond. The law captures how two measurements stay linked over many trials. At its base, that is all a law ever is, a stable connection between quantities. Now comes a part that often surprises people. Laws do not describe events. They describe limits. A law draws boundaries around which relationships are allowed to exist. Inside those boundaries, many outcomes remain possible. Outside them, nothing ever appears, no matter how carefully the setup is arranged. That explains why laws feel strict without being detailed. They do not tell you what will happen next. They tell you what will never happen at all. This role becomes clearer with conservation laws. Energy provides one example, but the same structure appears with momentum, electric charge, and rotation. These quantities move between objects, change form, or spread out, yet the total remains fixed. Nothing in the system tries to keep the total unchanged. The conservation appears only after everything settles. If an experiment ends with extra energy appearing from nowhere, the response is not excitement. The response is error, because the law does not bend. This shows another important feature. A law does not care about size. The same relationships apply to falling stones, moving planets, vibrating atoms, and distant galaxies. The numbers change, the units change, the surroundings change, the relationship stays. That wide reach is not assumed. It is earned through testing in many different situations. This is another place where expectations fail. People often expect rules to come from purpose or design. Physical laws come from neither. They are noticed because even disorder respects them. Chaotic systems obey laws just as strictly as neat ones. Wild air motion follows the same equations as smooth flow. A crashing wave respects conservation just as much as a clockwork machine. The law does not disappear when behavior looks messy. It remains in place because it never depended on tidy outcomes. This leads to an important clarification. A law does not guarantee prediction. It guarantees constraint. You may fail to predict what happens next, while still knowing certain outcomes will never appear. That certainty is where physics draws its strength, and this is where the word law earns its weight. A physical law is the strongest claim science makes, stronger than a model, stronger than a story, stronger than an explanation. It says, across all tested cases, under all accessible conditions, this relationship holds without exception. That does not make laws untouchable. New discoveries can refine them or reveal deeper structures beneath them. Even then, the older law survives inside its tested range. Newton's laws still guide bridges and baseballs. Ohm's law still guides circuits. Thermodynamic laws still govern engines and cells. The law remains because it was never about perfection. It was about consistency. At the deepest level, A law in physics is a statement about what stays fixed while everything else rearranges. It is the frame holding change together. And that brings back the question quietly waiting underneath all of this. If laws describe consistency rather than control, why does the universe show consistency at all? That question stays because laws do more than describe stability. They shape how reasoning itself works in physics. When a physicist faces a new situation, the first step is rarely prediction. The first step is elimination. A law immediately rules things out. You may not know what will happen when systems interact, but a law tells you what outcomes cannot appear under any arrangement. That power comes from the fact that laws apply before details are filled in. They operate at the level of structure, not outcome. This is how laws actually get used. Suppose two objects collide. You may not know their final speeds. You may not know the direction they move afterward. But conservation laws already fix the range of possibilities. Energy and momentum place boundaries around every allowed result. Any answer outside those boundaries is dismissed instantly, no matter how clever the explanation sounds. The law does not predict a single future. It restricts the space of futures. This is why laws remain useful, even when prediction fails. Weather cannot be forecast perfectly. Turbulence resists exact calculation. Human motion is wildly complex. Yet every one of these systems still obeys the same laws. Even when outcomes vary, relationships stay intact. This leads to a surprising result. Uncertainty in outcomes does not weaken laws. It highlights their role. A law remains exact, even when predictions are rough. That feels backward at first. People often expect exact laws to produce exact answers. Physics shows the opposite. Laws define constraints so strong that even randomness cannot escape them. This is easiest to see in statistics. Take a gas. Individual molecules move unpredictably. Collisions vary. Paths twist endlessly. Yet pressure, temperature, and volume stay linked by precise relationships. The law does not follow single particles. It governs the collective behavior without tracking details. Nothing in the gas coordinates. Nothing averages on purpose. The law emerges because every motion still respects the same restrictions. Here, a law does not describe what each piece does. It describes what the whole cannot avoid doing. This is one of the most counterintuitive features of physical laws. They grow stronger as systems grow more complex. That strength leads to consequences that often surprise people. One of them is this: multiple laws apply at the same time. No system ever follows just one law. A falling object respects gravity, energy conservation, momentum conservation, and constraints imposed by material strength all at once. These laws do not compete. They intersect. Each one trims the list of possible behaviors further. The final outcome sits at the intersection of all constraints. This is how physics stays coherent. You do not choose which law applies. All relevant ones apply together, automatically. The result is not negotiated. It is determined by compatibility. This explains why adding information does not remove laws. It narrows possibilities. Another surprising result follows from this. A law can remain correct even when the explanation behind it changes. This happens repeatedly in physics. Newton's laws described motion accurately long before deeper theories existed. Later work revealed broader frameworks that changed how motion was explained, yet Newton's laws stayed valid within their tested range. They never stopped working. They simply stopped being the deepest description available. That tells us something important about what laws are. They are not guesses about hidden causes. They are records of consistency. That is why laws age well. Now consider a paradox people often stumble into. If laws are descriptions written by humans, why do they feel so absolute? The answer lies in their origin. A law is not declared after a few successful tests. It survives relentless attempts to dismantle it. Physicists try extreme conditions, unusual materials, edge cases, and clever tricks. The law earns its status by refusing to fail. This gives laws a special role. They are not opinions strengthened by agreement. They are conclusions strengthened by resistance. That resistance shapes meaning. A law tells you something about the universe that remains true regardless of preference, perspective, or scale. It tells you reality has structure that does not bend to narrative. That realization carries weight beyond equations. It tells you the universe is not arbitrary. Events may appear chaotic, unpredictable, or complex, yet they unfold inside boundaries that never move. That makes explanation possible at all. Without laws, there could still be events. There could still be motion. There could still be change. But there could be no science. No comparison would hold. No experiment would repeat. No lesson would carry forward. A law gives memory to the universe. It allows the present to resemble the past in specific ways. And now the meaning comes into view. A physical law says that beneath all variation, something stays fixed. It says that while appearances change, relationships endure. It says that the universe does not reinvent itself moment to moment. That does not remove mystery, it sharpens it. Because laws answer how behavior stays linked while leaving the deeper question open, why this structure exists at all. Physics does not claim to answer that fully. It claims something narrower and more solid. It claims that whatever the universe is doing, it does so within limits that never waver. Those limits are what we call laws. They are not the actors in the story. They are the grammar. Without grammar, sounds still exist. With grammar, meaning appears. In the same way, events still happen without explanation. With laws, those events become intelligible. And that is why laws sit at the center of physics, not as commands, not as causes, not as decorations, as the unchanging framework that allows change to make sense at all. That realization tends to pull people forward because it suggests that learning physics is not about collecting facts. It is about learning the boundaries within which every fact must live. And those boundaries remain even as knowledge grows, even as explanations deepen, even as the universe continues doing what it has always done, behaving consistently without asking permission. At this point, the role of a law in physics comes into view without decoration. A law is not a belief about how the universe should behave. It is a record of how the universe has behaved every time we have been able to test it across places, scales, and conditions. It is a statement of consistency that reality keeps confirming. That consistency is what allows physics to function at all. After a law is established, it turns into a tool. It allows reasoning without seeing the outcome first. It allows confidence that certain results will never appear, even when the exact result remains unknown. That is the practical strength of a law. It does not describe the future in detail. It limits the future to a narrow range of allowed outcomes. This explains why very different systems can be discussed using the same laws. A swinging pendulum, a satellite orbit, and an electron bound in an atom behave differently, yet they remain tied to the same constraints. Surface details vary, the relationships remain. This also explains why laws survive progress. When physics advances, earlier laws are not discarded the way mistaken ideas are. They remain valid within the range where they were tested, even as broader descriptions add more structure underneath. Bridges still stand because Newton's laws hold. Circuits still function because electrical laws hold. Engines still run because thermodynamic laws hold. That persistence tells us something important about what is solid knowledge. Certain relationships hold without exception in every experiment performed so far. Energy does not appear from nothing. Momentum balances during interaction. Electric charge remains conserved. These statements are not guesses. They are the strongest claims science makes. At the same time, there are limits to what is known. Physics does not explain why the universe has laws rather than complete disorder. It does not explain why these particular relationships exist instead of others. It does not explain why consistency exists at all. Those questions remain open. That boundary between what is established and what remains unanswered is part of the structure, not a weakness. Laws tell us how far reasoning can go without speculation. They mark the edge where description ends and deeper explanation has not yet arrived. Taken together, this forms a clear world view. The universe is not free of constraint, and it is not fixed down to every detail. It operates within strict limits while allowing variation inside those limits. Events can surprise, yet they never violate the relationships holding everything together. That balance explains why prediction can be difficult while reliability remains absolute. It also explains why progress in science comes from tightening constraints rather than adding stories. Each new law or deeper version of an existing one removes possibilities rather than increasing them. That narrowing is progress. The takeaway is simple and strong. A physical law is the strongest form of knowledge available about the world. It does not tell us everything. It tells us what reality never does. That is enough. Because knowing what cannot happen allows technology to function, explanations to hold, and learning to continue without collapse. The universe may remain incomplete to us, but it is consistent. It behaves in ways that can be relied on, and every time a law holds, it confirms the same fact. The world is structured in a way that allows it to be studied, shared, and explained, again and again, without exception. A particle is often treated as the simplest thing physics can talk about. Something small, something localized, something that exists in a definite place and moves through space the way objects do at everyday scales. That assumption feels natural because much of classical physics is built on it. Careful measurement forced that assumption to be reconsidered. Particles did not behave like smaller versions of familiar objects. The more precisely their position was examined, the less their behavior matched the idea of a single, well-defined location. Attempts to track their motion stopped resembling continuous paths and started producing distributions instead. The description that worked in one experimental setup failed in another. That created a problem because physics depends on descriptions that hold across different situations. Instead of acting like tiny solid objects, particles produced statistical outcomes. They generated interference effects. They behaved as if multiple possibilities were involved before an interaction occurred, yet each interaction produced one specific result: a flash, a click, a mark on a detector. Something extended through space, something registered at a single location. Both features appeared in experiments. Removing either one broke the agreement between theory and observation. The meaning of particle had to change. A particle came to be treated as a repeatable physical event rather than a miniature object. It is defined by how it participates in interactions and how it shows up in measurements, not by a permanent shape or a fixed trajectory. It behaves consistently under the same conditions, even though its behavior cannot be reduced to ordinary motion. This explains why particles pass through matter without damage, why they can be created from energy, and why they can vanish in interactions without leaving pieces behind. Their behavior follows strict physical rules, but those rules are not the rules of solid objects. Space itself plays an active role. It carries physical properties and supports fields. These fields can be excited, and those excitations are what physics identifies as particles. Each particle corresponds to a specific kind of excitation with well-defined properties. This is why every electron is exactly identical to every other electron, not similar, exactly the same. They are not individual items with separate histories. They are the same physical occurrence appearing wherever the conditions allow it. Particles are not mysterious pieces of matter. They serve as the way the universe organizes interactions into discrete, countable events, rather than letting them dissolve into continuity. That perspective opens a deeper question, one that changes how existence itself is described. If particles are events rather than objects, what does it really mean for something to exist? To answer that, the safest move is to strip the word particle down as far as it will go and rebuild it carefully without relying on pictures borrowed from everyday life. At the most fundamental level known today, a particle is not a tiny object moving through empty space. It is a localized excitation of a physical field. That sentence sounds abstract, so let's slow it down and unpack it piece by piece. Physics describes the universe in terms of fields that exist everywhere. There is an electron field, a photon field, a quark field, and others. These fields are not things placed inside space. They are part of what space itself contains. They assign physical properties to every location, even when nothing dramatic seems to be happening there. Most of the time, these fields sit in their lowest possible state. Nothing noticeable occurs. But under the right conditions, a field can be excited. That excitation carries energy, momentum, and other properties. When such an excitation appears in a detector in a consistent, repeatable way, physics labels it a particle. So a particle is not something inside the field, it is something the field does. That distinction matters. It explains why particles are identical. Every electron carries the same charge and mass because each one is the same excitation of the same field. There is no manufacturing process, no variation, no individuality to account for. The field allows only one version of that excitation. It also explains why particles can be created and destroyed. When enough energy is supplied, a field can support an excitation. When that energy is removed or transferred, the excitation disappears. Nothing breaks. Nothing leaves fragments behind. The field simply returns to a lower energy state. This already contradicts a deeply rooted expectation that existence requires a permanent object. In modern physics, existence is tied to allowed activity within fields, not to enduring material pieces. Now let's look at motion. A particle is often imagined as traveling along a path, occupying one position after another, like a bead sliding on a wire. That picture works for baseballs and planets. It does not survive careful experiments at small scales. When physicists attempt to track a particle's position over time, the results do not trace out a single line. Instead, they form probability distributions. Predictions succeed only when the particle is treated as something spread out during its evolution, even though measurements always record a localized outcome. This is not a failure of instruments. It is not due to disturbance or lack of skill. It reflects how excitations of fields behave. Between interactions, the excitation is described by a mathematical object that encodes all the possible ways it could appear if measured. That description evolves smoothly and predictably. When an interaction occurs, one specific outcome is recorded. The rules governing both stages are precise and well tested. Trying to force this behavior into the picture of a tiny object following a hidden route leads to contradictions. Predictions fail. Experiments disagree. The idea of a particle as a small moving thing simply does not carry enough structure to describe what actually happens. This is where everyday reasoning runs into trouble. Everyday reasoning assumes that things have properties whether or not they are measured. It assumes position, motion, and identity exist independently of interaction. At small scales, those assumptions break down. Properties are not attached permanently to a particle. They are defined through interaction. A particle does not carry a position the way a coin carries a scratch. Position is something that appears when the particle interacts with something capable of registering location. The same applies to momentum, energy transfer, and other measurable quantities. That does not make particles vague or ill-defined. It makes them context-dependent in a precise way. This is why physics can calculate particle behavior with extraordinary accuracy, while everyday descriptions fail. The calculations are built around fields, excitations, and interactions. The everyday pictures are not. There is another point that often causes confusion. Particles are sometimes described as waves. This does not mean a particle is a ripple in water or a vibration of matter. It means the mathematical description governing how a field excitation evolves resembles the equations used for waves. The similarity lies in structure, not substance. The wave-like aspects describe how possibilities spread and combine. The particle-like aspects describe how interactions register as discrete events. Both aspects refer to the same underlying entity. Refusing either description leads to errors. Keeping both leads to reliable predictions. At this stage, the concept of a particle should feel less like a thing and more like a rule-based occurrence. It is defined by the field it excites, the properties that excitation carries, the ways it can interact, the consistent manner in which those interactions appear. Nothing extra is added, nothing vague is required. Particles are how the universe packages interactions so that energy, momentum, and information move in discrete amounts rather than flowing without limit. They are countable not because someone decided to count them, but because the underlying fields allow only certain excitations and forbid others. This is why particle physics works so well. It does not rely on analogy, it relies on constraints. And that leads naturally to a deeper realization. If particles are excitations of fields, and fields fill all of space, then what appears solid, separate, and object-like at large scales is built from processes that are anything but. Matter is not assembled from tiny stones. It is assembled from permitted activity. That idea does not weaken the concept of a particle. It makes it strong enough to describe reality accurately. That conclusion places particles as expressions of a deeper physical structure rather than the final layer of description. Once fields take center stage, many puzzles that seemed disconnected begin to line up. Creation and disappearance of particles no longer feel dramatic. High-energy collisions and accelerators convert concentrated energy into new excitations. Detectors register them. Later, interactions transfer that energy elsewhere and the excitations fade. Nothing mysterious enters or leaves reality. The accounting remains exact because the fields never vanish. This perspective also explains why empty space refuses to behave like emptiness. Even in regions stripped of matter, fields remain present. They fluctuate. They carry structure. Those fluctuations influence measurable outcomes, from forces between objects to the stability of atoms. Space functions less like a container and more like an active participant. Another consequence follows directly. Particles possess properties only because the fields enforce them. Charge, mass, and spin arise from how an excitation couples to other fields. The values appear fixed because the rules allow no alternatives. Nature does not choose an electron's charge. The field permits only that option. Attempts to picture a particle as a tiny solid core quickly fall apart here. Solidity emerges only when enormous numbers of excitations lock together through electromagnetic interactions. At smaller scales, nothing behaves like a hard object. Interactions dominate. Resistance, rigidity, and contact emerge later as collective effects. This explains why particles pass through one another so easily. Two excitations can occupy the same region of space because fields overlap without obstruction. Interactions occur only when coupling rules allow them. Without coupling, nothing collides, nothing bounces, nothing blocks the way. The idea of location changes as well. A particle appears at a specific place when an interaction occurs that transfers energy locally. Between interactions, the excitation remains distributed according to strict mathematical rules. That distribution does not represent ignorance or lack of information. It represents the full physical description available. Here, everyday reasoning struggles, because everyday reasoning treats properties as permanent possessions. In particle physics, properties appear through interaction. Position arises when something records position. Momentum arises when something exchanges momentum. Energy transfer defines energy measurement. Remove the interaction and the property loses operational meaning. This does not weaken prediction, it strengthens it. Calculations based on field behavior predict outcomes with precision unmatched by any classical picture. Particle accelerators, semiconductor devices, and medical imaging all rely on this framework working exactly as described. Another common expectation fails at this point, the idea that smaller always means simpler. Particles appear small, yet their description requires layers of structure absent from larger objects. A rock follows simple equations because internal complexity averages out. A single excitation exposes the full machinery. This also clarifies why probability enters the story. The equations governing fields do not predict single outcomes, they predict distributions of outcomes. Each interaction selects one allowed result. Repeat the process many times, and the distribution emerges with remarkable consistency. Probability here reflects structure, not ignorance. The rules constrain outcomes so tightly that the statistical pattern remains fixed across experiments. Randomness appears only within boundaries that never shift. At this stage, the word particle serves a very specific role. It labels a unit of interaction that carries definite amounts of conserved quantities. Energy arrives in packets. Momentum transfers in packets. Charge exchanges in packets. Fields enforce this discreteness. Without particles, interactions would smear continuously. Energy would leak without limit. Stability would collapse. Atoms, chemistry, and matter would fail to form. Particles exist because the rules require discrete carriers. This also explains why particles feel countable. Counting does not impose discreteness. Discreteness allows counting. One excitation registers as one event. Two excitations register as two. No interpretation required. Even forces look different from this viewpoint. Forces describe how field values change across space. Particles respond by exchanging excitations. What feels like attraction or repulsion arises from permitted exchanges governed by symmetry and conservation. The language of particles survives because it remains useful. Detectors click, tracks appear, experiments record events. Talking about particles keeps communication efficient. But beneath that language lies the field-based structure doing the real work. This dual description causes confusion only when taken too literally. Treating particles as tiny objects leads to contradictions. Treating them as abstract mathematical ghosts misses their tangible effects. The field excitation view holds both sides together without strain. At larger scales, this picture fades into familiarity. Vast numbers of excitations interact, average out, and lock into stable arrangements. Tables resist pressure. Walls block motion. Objects occupy locations persistently. None of this contradicts particle physics. It emerges from it. Seen from far enough away, the details disappear. Seen closely, the machinery shows itself. Particles therefore occupy a precise conceptual role. They mark where and when interactions register. They carry conserved quantities between systems. They arise from fields and return to fields without residue. Nothing extra hides underneath. Nothing simpler waits beyond. That realization changes how matter, space, and interaction fit together. Reality does not consist of objects floating in emptiness. It consists of structured activity governed by rules that allow certain excitations and forbid others. Particles sit at the boundary between possibility and record. They translate continuous field behavior into discrete events that can be counted, measured, and compared. That role explains their strange behavior without reducing it. It also explains why attempts to force them into everyday categories repeatedly fail. The universe does not operate on familiar categories at small scales. It operates on permission and constraint. Particles simply follow those permissions with absolute consistency. At this stage, the picture is complete enough to use with confidence. Particles are not tiny, solid pieces hidden inside matter. They are localized excitations of fields that exist throughout space. Fields determine which excitations are allowed, which properties they carry, and how they interact. When an excitation transfers energy, momentum, or charge in a measurable way, physics records that event as a particle. This framework explains why particles are identical, why they can appear and disappear, why they pass through one another, and why interactions occur only under specific conditions. No extra ingredients are needed, no internal cores, no missing mechanisms. What physics knows with very high confidence is how particles behave, how they are produced, how they interact, and how their properties arise from fields and symmetries. These descriptions are tested continuously in particle accelerators, laboratories, electronic devices, and medical imaging systems. The agreement between prediction and measurement reaches levels of precision unmatched in other areas of science. Physics also knows that particles are not the final layer of description. They are effective representations of deeper structures. Fields underlie them. Symmetries restrict those fields. Conservation laws limit what can occur. This hierarchy is not philosophical preference. It is enforced by experimental results. What physics does not yet know is why the fields have the specific properties they do. It does not know why these fields exist instead of others, or why their strengths take the particular values measured. A complete framework that unifies all known fields at every scale has not yet been achieved. These limits are clearly recognized rather than hidden. That distinction matters. Physics is not uncertain about particles. It is precise about where certainty ends. From this perspective, matter is not assembled from rigid pieces stacked together. It arises from repeated interactions that remain stable because the rules allow them to. Solidity, shape, and persistence emerge from enormous numbers of excitations exchanging forces in tightly constrained ways. At larger scales, the details average out. At smaller scales, the underlying structure becomes visible. This also explains why the same particle language applies across very different situations. The electron in a wire, the electron in an atom, and the electron recorded by a detector are not different entities. They are the same excitation interacting within different environments. The surroundings change, the governing rules do not. The takeaway is direct and practical. Particles are how the universe makes interactions discrete. They are how conserved quantities move in finite amounts. They permit stability without locking everything in place, and variation without losing order. Without them, atoms would not hold together, chemistry would not operate, and matter would fail to persist. Thinking this way replaces the image of a universe built from tiny objects with one built from a loud activity. Nothing becomes vague, nothing loses precision. The description gains consistency across scales. When physics speaks about particles, it is not describing little things darting through empty space. It is describing how the underlying structure of reality registers interactions in countable, reliable ways. That perspective does not make the world harder to deal with. It makes the world workable. Let's talk about something that sounds ordinary, almost boring, yet sits underneath nearly everything physics says: the idea of a state. A state sounds like a condition, a description of how something is right now. But in physics, it carries a precise meaning. A state is the full physical situation of a system, written in the smallest amount of information needed to determine what can happen next. Physics has a strict rule here. It does not care about how a system arrived where it is. It only cares about how it is right now. If two situations are physically identical at this moment, physics treats them as the same, even if their histories were wildly different. A short example makes this concrete. Think about a cup of coffee on a table. To predict what happens next, physics does not need to know who brewed it, what cafe it came from, or how tired you are. What matters is whether it is hot or cold, how much coffee is there, and the surrounding room temperature. If two cups match in those properties, physics predicts the same cooling behavior for both. The story behind them disappears. Only the present description remains. That present description is the state. This idea reaches far beyond coffee. A moving ball, a gas in a room, a planet in orbit, all of them are treated the same way. Physics asks a single question: what information is required to fix the future behavior? Everything else is ignored, not out of laziness, but because it has no physical effect. This is where people often hesitate. It feels like something must be missing. Surely reality carries more detail than a short list of numbers. Yet experiments keep agreeing with physics. If a detail cannot influence what happens next, it does not belong in the state. A state is not a photograph. It is a working summary. It contains exactly what the laws of nature can act on, and nothing more. That makes states powerful and also a little unsettling. It means the universe carries itself forward moment by moment without consulting its past, except through what the current state already holds. Everything that can happen next depends on what fits into that description, and nothing else. So let's slow this down and take it apart carefully, because this is where the word state stops sounding ordinary and turns into something precise. At the most basic working level, a state is the complete physical condition of a system, expressed in a form that allows the laws of physics to operate without guessing. It is not a picture, not a label, and not a story. It is a set of facts that fully fixes what the system can do next. That word complete is doing real work here. Complete does not mean detailed in a human sense. It does not mean rich, expressive, or emotionally satisfying. It means that if you hand this description to the laws of physics, they do not ask for anything else. No extra information, no missing inputs, no follow-up questions. If some detail can affect what happens next, it belongs in the state. If it cannot, it does not. That rule sounds obvious until you apply it seriously. Return briefly to the coffee. Suppose two cups sit on the same table. One was brewed 5 minutes ago, the other an hour ago. One was stirred clockwise, the other counterclockwise. One came from a cafe, the other from a kitchen. None of that enters the state. If the temperature, the amount of liquid, and the surrounding air are the same, physics predicts the same cooling behavior. The rest feels important to us, but it has no physical leverage. That difference between what feels real and what can influence future behavior is where many people get lost. Physics has learned to be ruthless about it because prediction depends on it. This tells us something crucial about what a state actually is. A state is not how things look, it is how things are positioned relative to the rules. That is a very different notion. It trades rich description for functional sufficiency. This is why states so often look like a short list of numbers, not because reality is simple, but because most details cancel out when it comes to future change. People often expect that more description should always improve prediction. Physics finds the opposite. Extra description often adds noise without adding power. States are minimal on purpose. Now follow the consequences of that idea. Any change you can think of, motion, heating, mixing, decay, growth, can be described as a transition from one state to another. The laws of physics are nothing more than rules that map one state into the next. This reframes the entire structure of physics. Instead of objects being pushed around by laws, you get states being updated by rules. Instead of causes acting on things, you get present conditions fixing future conditions. Take memory. People often speak as if physical systems remember their past. Physics says something stricter. Any trace of the past must be encoded in the current state. If it is not encoded there, it has no effect on what follows. A stretched spring carries information about being stretched because its present shape contains it. A scar carries information about an injury because the tissue structure contains it. A cooled cup of coffee carries no information about how hot it was an hour ago because nothing in its present condition encodes that fact. Memory in physics is not a mysterious faculty. It is information stored in a state. This leads to a result many people resist. The past has no direct influence on the present. Its influence exists only through what survives in the current state. If nothing survives, the past is physically silent. This is not a philosophical preference. It is forced by how prediction works. If two systems share the same state, physics gives them the same future. No experiment has ever contradicted this. Now let's push deeper into what a state is, not just how it behaves. A state is an abstract object. That word often raises eyebrows, but here it means something very specific. The state is not located in space the way the system itself is. The system exists in space. The state exists in the space of possible conditions. Those are different arenas. A ball travels through space. Its state lives in a mathematical space whose coordinates represent position and motion. A gas fills a room. Its state lives in a space defined by quantities like temperature, pressure, and density. The system and its state are related, but they are not the same thing. This distinction becomes important as systems grow large. A gas contains an enormous number of particles, far too many to track individually. Still, it has a state. Physics uses collective quantities because they preserve predictive power. The full microscopic detail exists, but the state that physics actually uses is compressed. This reveals another sharp lesson. A system always has a state, even when no one can write it down. Existence and accessibility are not the same. Weather has a state. We measure parts of it, approximate others, and still get surprises. The laws did not fail. The description was incomplete. This reframes uncertainty in a very concrete way. Uncertainty is not something floating over reality. It is a mismatch between the actual state and the state we are able to specify. Physics never becomes confused. Descriptions do. This also explains why physics places so much emphasis on initial conditions. Laws by themselves do not produce specific outcomes. They only specify how states change. Without a state to act on, laws describe possibilities, not events. People often ask why the laws of physics do not explain everything. The answer is blunt. Laws do not select states. They transform them. The universe does not ask the laws what state to be in. It already is in one. Now bring this picture into modern physics. In quantum mechanics, the state takes a form that resists everyday language. It does not assign definite values to properties like position or motion. Instead, it encodes the full structure of possible outcomes. Yet its role remains unchanged. The quantum state still contains everything physics can say about what follows. Nothing extra can be pulled from it. Nothing less will suffice. This result bothered many brilliant physicists. They suspected hidden layers beneath the formalism. Decades of experiments answered the same way. Predictions match the quantum state exactly, and no hidden layer reveals itself. Once again, physics encountered the same lesson. Reality provides exactly the information it uses, and no surplus. Here, the idea of a state stands out as more than a technical detail. It holds the structure of physics together. The universe advances by carrying forward a compact description of itself. Each moment inherits only what the present state contains. Everything else drops out of physical relevance. This does not make reality thin, it makes it efficient. And now something subtle but powerful comes into view. If the state contains all that can influence what follows, then the question, what exists, quietly transforms into what can affect future change. In physics, existence and influence are inseparable. That single move explains why some things that feel important never appear in equations, while some abstract symbols carry enormous predictive force. Physics follows influence, not impression. State is not jargon at all. It is the mechanism by which nature carries information forward in time. And with that backbone in place, a further tension comes into view, one that appears when the very notion of a single definite state begins to strain under it. From here, the idea of a state stands at the center of how physical influence is organized. If influence must pass through the state, then anything that fails to register there cannot affect what follows. This draws a hard boundary around explanation. Physics does not ask what might have played a role. It asks what is encoded right now in a way that constrains the next moment. This changes how cause and effect are treated. Causes are not events reaching forward from the past. They are features of the present state that limit what can happen next. Effects are not produced by history pushing forward. They are produced by rules acting on current conditions. That view clashes with everyday habits of thinking. People tend to place causes in stories about what happened earlier. Physics places them in the present description. This difference is structural, not linguistic. Now look at systems where states react strongly to small differences. In chaotic dynamics, extremely tiny variations in the state lead to wildly different outcomes. Weather illustrates this well. Two atmospheric states that differ by amounts far below any practical measurement can lead to entirely different futures. The rules remain exact. Nothing about the laws breaks. The difficulty lies entirely in the state itself. Here is the striking result. Rule-based evolution survives even when prediction fails. The system follows its laws perfectly, yet foresight collapses because the state cannot be specified with enough precision. Unpredictability in this sense does not signal disorder, it signals sensitivity. This separates two ideas that are often mixed together. Lawfulness describes how states lead to states. Predictability describes whether those transitions can be tracked with the information available. One can hold without the other. Now move to smaller scales. Quantum physics accepts the same framework and then stretches it in a way that defeats familiar expectations. The quantum state does not list properties as fixed facts. It does not supply a definite position or motion ahead of interaction. Instead, it encodes how the system can respond when interaction occurs. This is not vagueness, it is precision of a different kind. The quantum state contains everything that can shape outcomes. It simply refuses to supply values that have no physical role until interaction takes place. This leads to one of the most surprising consequences in physics. The same state can give rise to different outcomes depending on how it is probed. The outcome is not stored in advance, it is selected through interaction. For a long time, many physicists expected a deeper layer that would restore familiar descriptions. Experiments repeatedly blocked that route. Predictions drawn from the quantum state matched reality exactly, and no hidden layer ever showed itself. Here, the meaning of a state sharpens further. It is not a list of attributes, it is a constraint on possible futures. Nothing outside that constraint appears in outcomes. This reworks causation again. There is no side channel through which influence travels beyond the state. No invisible mechanism supplements it. Influence passes forward only through what is encoded at each moment. This also explains why higher-level sciences remain valid without conflict. Chemistry, biology, and neuroscience all describe states, just not microscopic ones. A chemical state summarizes bonding arrangements. A biological state summarizes metabolic activity. A neural state summarizes electrical and chemical activity across networks. Each level tracks influence relevant at its scale. None violate physics because each respects the same rule. Future behavior is limited by present conditions. Reduction does not erase these descriptions, it anchors them. Now a natural puzzle emerges. If states carry everything relevant, and if laws act uniformly, why does the future ever feel open? Why does novelty appear at all? The answer lies in complexity rather than indeterminacy. Even systems governed by strict rules can generate behavior that resists anticipation because the space of possible states is enormous. Rules apply locally, but their repeated action produces outcomes that exceed simple forecasting. Nothing extra is added. What already exists rearranges itself in ways that overwhelm tracking. This explains why surprise persists even in a lawful universe. Surprise reflects limits on access to states, not failures of the rules. At this stage, the idea of a state carries weight beyond calculation. It implies that reality advances by carrying forward exactly what can influence what follows, no more and no less. The universe operates with strict economy. That economy explains both the reach and the restraint of physics. Reach comes from focusing only on influence. Restraint comes from ignoring everything else. The picture that emerges is stark but coherent. Reality is not driven by hidden narratives or accumulated intentions. It proceeds through continuous updates of states under fixed rules. Every moment inherits a complete description of what can shape the next one. Everything else, no matter how compelling, plays no role. This does not strip the world of richness. It explains how richness arises without extra machinery. With this framework in place, one issue stands ahead. Measurement itself must be treated as a physical process, subject to the same rules and the same limits. That issue waits just beyond this point. Measurement brings the framework to completion without adding anything new to the rules. When a system interacts strongly with another system, the two no longer carry separate descriptions. Their physical conditions become linked. From that point onward, there is a single, combined description that governs what can happen next. This is not a special category of event. It is the same kind of update that occurs in every physical process. Measurement does not reveal a pre-written answer. It creates a new situation by coupling systems together. This fact removes a long-standing confusion. There is no divide between natural evolution and observation. Both are physical interactions. Both follow the same laws. Both operate by updating states. With that, the picture closes cleanly. Physics rests on a small set of claims that have survived every test placed against them. Every physical system carries a complete description of its current condition. The laws of physics operate only on that description. What happens next depends only on that description and the laws. Anything not present in that description cannot influence future behavior. These statements are not philosophical positions. They are the conditions required for prediction, explanation, and consistency to function at all. There is also a crucial distinction that keeps reappearing across physics. A system can have a well-defined description even when no one can specify it fully. Limited access restricts forecasting, not the behavior of the system itself. Nature does not wait for complete information in order to proceed. This explains why lawful behavior continues even in situations where outcomes appear surprising or irregular. There are also boundaries worth stating clearly. Physics does not claim that current descriptions of states are final. Classical descriptions were replaced by quantum ones. Future theories may alter the form again. What cannot be removed is the role these descriptions play. They carry all physically relevant influence forward. Physics also does not claim to explain why the laws take their particular form. States describe how change unfolds under given rules. The origin of those rules remains beyond experimental reach. And physics does not require a single, uniform description across all scales. Instead, it supports compatible descriptions at different levels, each tracking influence appropriate to its domain. These limits are not weaknesses. They define where physics is precise and where it remains silent. Now assemble the full view. The universe is not best captured as a collection of objects accumulating properties through time. It is better captured as a continuous progression of physical conditions, each one determining what can follow. Laws act as update rules, transforming one description into the next. Nothing outside that process plays a role. This explains why physics favors compressed descriptions. It explains why distant histories fade while present conditions dominate. It explains why chemistry, biology, and neuroscience coexist without conflict, each using descriptions suited to their scale while remaining physically grounded. It also explains why explanation has sharp limits. Physics can state what follows from what and what cannot follow at all. It does not promise narrative satisfaction. It promises internal consistency. The takeaway is direct. Reality advances by carrying forward only what can influence what comes next. If something shapes the future, it appears in the current description. If it does not appear there, it has no physical effect. That single principle replaces countless informal assumptions with one disciplined framework. The world then reads not as a buildup of past events, but as a continuous handoff, each moment passing forward exactly the information required for the next, and nothing beyond that.
If you think you're dumb, congratulations. You just proved you can think. Because the real fool is the one who never asks anything. You're not dumb, and I'm going to prove it to you right now. Every human brain, without exception, starts with the same foundation. No brain comes with a label that says smart or stupid. Physics shows us that the brain is just like any other muscle in your body. If you train it, it grows. If you neglect it, it weakens. There's no fixed destiny written somewhere saying one person was born a genius and another was born to fail. What actually exists are thought habits that either strengthen or weaken your mental power. Now, imagine you never trained one of your legs. What would happen? You'd probably look like those gym guys who only work out their arms and completely forget about leg day. It would be weak, with no strength to run. But that wouldn't mean you were born without muscles. It would only mean you never trained them. The same thing happens with the brain. Most people simply don't train it the right way. They use their brain like a cheap calculator, not like a brilliant laboratory. That's why they feel slow, stuck, incapable. But the truth is, all it takes is changing the way you use your mind to realize you've got infinite potential inside you. Now pay close attention. The first thing you need to understand is that intelligence is not about memorizing facts. Intelligence is the ability to explain things in a simple way. The method is this: if you can't explain something to a child, you don't really understand it yet. And that's the first secret to proving you're not dumb. When you learn something, try to explain it out loud, as if you were teaching it. That's how you start working out your brain. Just don't forget to train your legs while you're at it, all right? Your brain is forced to organize the internal mess. It takes scattered bits of information like loose Lego pieces and has to build them into a coherent castle. This activates different areas: memory, language, creativity. It's as if regions that usually work separately suddenly come together in a grand orchestra. When you try to explain what you've learned, you're not just repeating it like a parrot. You're rewriting the knowledge inside your own head. And here's the key. If you want to learn any subject more easily, simplify it. The brain loves to turn everything into complications. It almost feels like the harder something sounds, the smarter a person thinks they are. But real intelligence is taking what's complicated and making it so simple that even a child can understand it.
Want to see it in action? Take a look at this little monster of an equation.
Beautiful, isn't it? Looks like something a NASA genius would scribble on a chalkboard. Just looking at it, most people freeze up and think, "That's it, I'm dumb, I'll never get this." But the truth is, what's really happening here is simple. All of that is nothing more than a complicated way of representing basic relationships between numbers. For example, right in the middle of all that chaos, you could say, this is just a fancy way of calculating the difference of two squares. And when you simplify it, it's really just x plus y. What looked like a mysterious equation is simply a sum in disguise. And that's the secret. When you simplify, the brain breathes. It understands the essence. Math isn't about memorizing giant formulas. It's about recognizing patterns. And the same goes for any field: physics, biology, finance. If you learn to search for the essence, the why behind things, suddenly everything becomes clear. No one is dumb when facing a hard problem. What we really have are bad explanations, messy and overcomplicated, that turn something simple into a maze. But when you force your mind to translate things into simple terms, you realize the brain was never the problem. The problem was always the way you were trying to learn. And it's not just in math. We simplify in physics, too. Someone walks in with authority and says, "The law of inertia describes that a body in motion tends to remain in motion." Sounds complicated, right? Want me to simplify? It's just this. If you kick a ball, it keeps rolling until something stops it. That's it. In biology, the same story. Someone says in a serious voice, "Photosynthesis is the biochemical process by which autotrophic organisms convert light energy." Phew, exhausting. Want the simple version? It's just the way plants invented to eat sunlight. Done. No mystery. And you know what's best about all this? This way of learning is actually more fun. Because let's be honest, traditional studying is boring as hell. It's like trying to memorize an entire phone book just to look smart. But when you learn to simplify, when you turn the complicated into something simple, that's when the real fun begins. That's the moment the genius is born, the one who enjoys asking questions, who smiles when discovering the why behind things, who takes pleasure in turning mystery into clarity. Learning is like playing, because when you're having fun, the brain doesn't see it as an obligation. It sees it as a game. And with games, we keep going. Have you noticed? You can play video games for hours without getting tired. But 15 minutes of a boring lecture feels like medieval torture. Why? Because games have challenge, curiosity, fun. When you bring that same spirit into your studies, you unlock a superpower. Imagine this. You take a tough math problem, or some crazy concept in physics, and instead of thinking, oh my God, I'll never get this, you think, okay, how can I turn this into a joke? How can I explain this to my 10-year-old cousin and make him laugh? In that moment, you stop being a slave to studying and start becoming its master. And then something magical happened. You actually start looking forward to the next problem. You get curious. You start laughing at your own discoveries. And it's at that exact point that the genius is born, when learning stops being an obligation and turns into fun. And here's the paradox. The secret of intelligence isn't memorizing answers, it's asking why. A person who asks too many questions might seem dumb to others, but what most people don't realize is that curiosity has been essential for every human discovery. If Isaac Newton hadn't asked, why did this apple fall from the tree instead of shooting up into the sky? Gravity might never have been formalized. Think about it. What everyone else saw as something ordinary, an apple falling, Newton turned into a question. And from that question came one of the most powerful laws in physics. Albert Einstein? He didn't create the theory of relativity because he memorized formulas. He started by asking, what if I could ride alongside a beam of light? What would I see? A crazy, almost childish question that any serious teacher would have called nonsense. But it was exactly that nonsense that opened the door to one of the most revolutionary theories in history. Even everyday inventions were born this way. Why does water heat up when it boils? Why can a piece of metal turn into an electric current? Why does sound move through the air? Every breakthrough that now feels obvious started with someone annoying the world by asking simple questions. What most people call stupidity is really just the inability to ask. And what they call genius is nothing more than stubborn curiosity. Newton wasn't magical. Einstein wasn't superhuman. They were just stubborn enough to keep asking when everyone else was saying, we already know that, stop bothering us. And here's the turning point. Genius is born when you take seriously the questions everyone else ignores. If the apple falls, ask why. If the shadow moves, ask why. If a 500-ton airplane flies while a little bird drops dead from a tree, ask why. The more you let those stupid questions bother you, the closer you are to brilliance. And here's a truth almost nobody talks about. You're not dumb for asking. You're only dumb when you care too much about what other people think of you. Because that, deep down, is what kills curiosity. You wanted to raise your hand in class and ask, but then you thought, they'll laugh at me. They'll think I don't know anything. But guess what? It's exactly by not asking that you stay not knowing it. A genius is the person who simply doesn't care. He asks, he gets it wrong, he gets it right, he asks again, until he understands. And here comes a crucial point, emotional intelligence. There's no use in training your brain if you're still a slave to other people's opinions. A brilliant mind isn't just one that understands physics or math. It's one that understands itself. It's the kind of mind that doesn't get shaken by stupid criticism, doesn't compare itself to the neighbor, and doesn't fall apart because someone said, that's obvious. Pay close attention now. Anyone who lives worried about judgment will never discover anything new. Every bold idea they have, their first thought is what their friends will say, what the family will say, what the experts will comment. The result? They spend their entire lives hiding their questions, and with them, hiding their true potential. You want to be seen as intelligent? Then stop trying to look intelligent. Focus on being curious, on simplifying, on laughing at your own mistakes, and on learning quickly. That is far more rare and far more valuable than pretending to know everything. In the end, the real genius is not the one with ready-made answers, but the one with the courage to ask, the discipline to search, and the maturity not to care about the audience. The same people who laugh at you today for asking will applaud you tomorrow for discovering what they never had the courage to look for. So, what should you start doing today to train your mind like a genius? First, cultivate curiosity. Ask why about everything, There's no such thing as a stupid question. There's only the fear of looking stupid. And you already know. You're not dumb for asking, you're dumb for caring too much about what others think. Second, practice simple explanation. Every time you learn something, try to teach it out loud as if you were explaining it to a child. If you can't, it means you don't really understand it yet. Go back, simplify it, and explain again. That's the workout that truly strengthens your brain. Third, take action. Just thinking isn't enough. Solve problems, write, test your ideas. Action is the final exam that shows whether you truly understood or if you were just memorizing. Fourth, practice concentration. Stop letting yourself get distracted every 5 minutes. When you focus on one single thing, your mind works like a laser. Fifth, build self-confidence. Don't wait for applause. Every genius has been called crazy at some point. The difference is they kept going anyway. Curiosity plus simple explanation plus action plus concentration plus self-confidence. That is the manual that proves you were never dumb. You just needed to learn how to use your brain the right way. And remember this, inside your head you carry the same kind of brain that wrote symphonies, that built rockets, that discovered gravity, that decoded DNA. You have a brain capable of finding the cure for cancer, of creating technologies that don't even exist yet, of transforming your life and the lives of millions of others. The problem was never you. The problem was believing you were limited, that you had no talent, that you weren't born a genius. But the truth is, the genius has always been inside you, waiting for you to stop being afraid to ask, to stop going silent in front of what you don't understand. Never forget, every time you ask why, you open a new door inside your mind. Each answer leads to another question, and it's in that endless path that the greatest ideas are born. The world is not driven by those who know all the answers. It is driven by those who have the courage to ask the right questions. So please, never stop asking why. Never let shame or judgment kill your curiosity, because it's exactly that curiosity, that restless spark inside you, that can change everything. You're not dumb. You never were. You're an explorer, and your mind is the greatest unexplored territory that exists. Take care of it, train it, simplify, focus, trust, and keep asking, because every single why could be the beginning of the next great discovery. And now I want you to do something simple but powerful. Leave your comment down below. Write, "I will never stop asking why." Declare it, because every word you write is a commitment to your own growth. And don't forget to like this video, because that shows it truly resonated with you. Subscribe to the channel to keep receiving content that challenges your mind and expands your worldview. Think about it. Maybe a single click today could be the start of a massive transformation in your life. So comment, like, subscribe, and hit the bell. Because here you don't just get information, you get tools to think like a true genius.